through because I really need to get you into the frame of mind of recalibrating and clarifying different things. So let's say that you have a problem like this. Shortly we're going to solve a problem like this. So it says many industrial objects have been considered as a composite body. So you know about composite body already. We know that in this we have 4 figures. Can you tell me the 4 without looking at the notes? What are the 4 just jumping out at you? What are the 4? Somebody tell me.
A rectangle,
Circle. So you see that
a
you have a
triangle,
semicircle,
yeah,
right? And you
yeah,
have what else?
a rectangle and a triangle,
Rectangle, triangle, right?
and a quarter circle.
And the quarter circle. Quarter circle. So we have 4 figures. So I say let's label it A, B, D, and E. They never bother use C. All right. So okay, good. So all right. So we're gonna look at it now. So it says that we must consider the particle. We have done that already. And this is you're gonna get a sheet similar to this in exam. In fact, it's going to be more comprehensive and it's gonna get about 2 to 3 sheets like these. One, when you look at this sheet,
3 sheets like this, sir.
yeah, you're gonna get one looking like this and some others. I think so. So this one will show you what is the X bar for the regular figure and the Y bar. It also will show you the inertia, right? So it's BH cube, and then for this, there is a little thing that I want to point out again, that with the direction that you look to change the H to the B, right? So because it switches. When you go in the y-axis, these quantities change around. This become H and this become B cube. So we
So
have some
it's
problem.
based on height.
Yeah, we're gonna look. We're gonna look at it and show you. For this is when you're finding the inertia of the for the y. So we're gonna look at a problem like this. This is your alpha circle. When you're finding the y bar, remember you use the formula over here, 4 upon r 3 pi. So that is our y. For x, you're using just the radius. So we're gonna look at a problem like that. And this is when you're doing the inertia now for a semicircle, this is what you use. For a quarter circle, these are the x bar and y bar. They are same quantities. So you need to look at it. When you're doing the inertia of a quarter circle, this is the formula. And for half circle, remember that you measure all the while from the back of the triangle, right? So it means that depends on where your origin is. Sometimes the triangle is turned at this tip here is turned. Are you seeing my pointer?
Yes, sir.
Yeah, so you see this tip sometimes is pointing to where the origin is. So it means that you'll use the 2/3 of the length up here rather than the 1/3 behind here. So it depends on how the figure is orientated. However, you use both 1/3 and 1/3, both for height and base. So you see it's equivalent to that formula. And the inertia of a triangle is 1 upon 36 BH cube. Right? And it depends if it switch again, you notice these quantities switch around. This become H and this become B cube. Same difference. So on a circle, it's really XX. The radius is typically X and Y bar, and the inertia is 1 upon 4 pi. Let's look at some problems now. And see, you're gonna get another sheet like this, have some more like that, and you're gonna get this. This will help you for I don't know if you will really use this as such. This is for when you find inertia of a mass. All right. All right. So you separate it into figures. Let's just look at this one now quickly now. So we already said that we separate into the triangle, rectangle, quarter circle, semicircle. All right. And there are some things that I want to point out to you. So all right, let's look at them now. We know that we have a semicircle. Like last night we looked at this in the other tutorial, so we'll go through quite a bit of questions. So look at this now. You have the first we have rectangle in the box, which is a segment. You have triangle. You have quarter circle. The Q in the box there over where you see the segments here. It means quarter circle. This it means quarter circle right here, right? And then you have the semicircle down here. So let's look keenly now. So for the area, right? You see, so when you calculate area of a rectangle, you put it here. So it is 6 times 3, because 3 is the height. Remember? So that 3 is the height. So 6 times 3 give you 18 for the area for the rectangle. What about the triangle? Triangle is 3 times 3, so it's half base times height, so that is going to give you 9, 3 times 3 is 9, half of 9 is 4.5, so the area is 4.5. The quarter circle, of course, you know that that is quarter, so it's pi r squared divided by 4, and so it's, you get 9 pi, and the radius is 3, so you get 9 pi divided by 4. For the semicircle, the same thing apply, pi r squared divided by 2 this time, so you all know that. But of course, look carefully, minus sign is introduced in the box. Why? Because it is a hollow, or we call it a void area. So it's not actually there. So that area will have to be subtracted from the total area. And therefore, that's how they got the 28. So they add the entire column here, remember? Add the entire column and you subtract that one. Don't add it. Make sure. All right, let's look on how we find X bar and Y bar for each figure. So first one, the rectangle is the easiest one. For the X, you know that this is what? 6. So half of 6 is 3. So that is 3 there. For the Y, the height is what? 3. So half of 3 is 1.5. So that's given. For the triangle now, watch this again. 1/3 of 3 is what? 1. Not true. So therefore, you see how you get the 7 here now? So this is 1 plus 6 give you 7 right here. Everybody see that?
Yes, sir.
Good. Next one. All right, the next one we will move on to is the circle. The quarter circle. So the quarter circle, what rules apply? What's the formula to get the quarter circle? Remember, so the quarter circle is going to be a distant here, map here now. So the distant, the X distant is this. And watch this carefully. Will this distant be a positive distant or a negative distant? You want that X bar and you want the Y bar here. This distant here is a negative distant. I gone over here. This is negative X axis. So the quantity cannot be positive. So see down there, first of all, the X bar, you'll employ the formula, which is 4r upon 3 pi. Everybody remember that? So see they put it down here. 4r upon 3 pi. That is what for a quarter circle. So, and it is minus because it's over the X side, the negative X axis. So it's 4 times 3 divided by 3 pi. So that is really 4 divided by pi. Right? Is that value because the 3's of course would cancel. All right. Next one, let's look at the Y for where are we? Where did I go? See, so we finished the rectangle, we don't the quarter circle. And by the way, for the quarter circle, it is both the same thing. Remember we saw it in the table. It's both Y bar is also 4r upon 3 pi. It's the same thing. So for this distance here, this distance coming up is the same as this. The X and Y, we use the same expression. But the X is negative because it's at the negative X-axis side of the frame. Remember now that the frame here, you know, is you have YX frame or frame of reference you're working with. This is Y. Come on. Where is it? This is Y. Y. And this is X out here. And those are positive. So those are, so this is why this going up, this Y bar going up is positive side. So it's positive. All right. When you finish that, let's move to the semicircle. What about the semicircle? The semicircle, for the semicircle, any semicircle you have, right, you're going to need to find that distance up there, which is your Y bar distance. Your Y bar is going to be equal to the same formula that we just used a while ago. 4r upon 3 pi. And for the X, it's going to be the radius of the circle. So this is going to be an X bar. So your Y bar is going to be that distance up the vertical distance. So that is your Y bar, right? So right there, you are able to, and look, why is this? Can somebody tell me that why is that X bar 0?
Sir, the X bar is at the origin, so it's origin point of the
perfect. Perfect. So therefore, that one intersect with the Y-axis and the X-axis. So right there, so it form a line of symmetry for the semicircle. It cut the semicircle in half, so it form a line of symmetry for the semicircle. So there, the x value has no value, but the y will have. It's the same formula to use, which is, see it up here, 4 times r, the radius is 1, divided by 3 pi. So that follows. And then now all we do, we multiply this column here by each one of the columns here. So the area is multiplying the x and y, and we get from that, for the AX, we get that column and then AY. So we keep multiplying the area by each one of the X bar, Y bar for the individual ones. And if you notice, the one for the quarter circle is minus right there. So it goes right through, right? So that means it will affect this component here, the AX component. So when you minus, you add those 254 plus 31.5, and you minus, you're going to get 76.5. And that's the total, that's the summation line of AX, A time X bar. And the same thing will go, if you notice, for the semicircle, this is minus. Why is this minus? Because the area, hold on, because the area is negative for the semicircle, then therefore this component here. So in fact, if x wasn't 0, it would also be a negative value. So it is 0, so you just add everything there. All right, and as a result of that, now we can simply find the centroidal axis. So x bar is going to be, this was the summation of the sum of xa divided by the total area. So each one of them, sum them and divide by the total area. So it is saying that the centroidal axis is at 2.73 for the x and 1.42, which you see it here. So it's basically your x is like there. Not drawn perfectly to scale, but this is 2.73 for that little distance there. And then your y distance is 2.73. All right, so that is y bar and x bar, and that is a centroidal axis. All right, let's take it from there. All right, and you know you can find the inertia of the figure by using the different formulas. All right, so let's move on. All right, let's look at this figure here now. You may never get something like this, but still we're gonna go through it quickly. All right, so a figure like this, it is said you have 2 blocks of different material and they are assembled as shown. The density of the material are, so you have density A and density B. So the A is 150 and it is in pound foot. And this one is 400. So this is an apparently heavier material. All right, so you must find the center of gravity, right, of the assembly. So you're gonna follow some steps here now to do it. All right, so in the solution, block A and B can be considered as 2 segments. So what we're gonna do is separate them into different segments, right? So this is like what you call a triangle prism, right? Something like that. And then you have, so it's separated right here. And along here you have a cuboid. So it's you call it a more rectangular cuboid you have around here. So this is more a triangle prism or something like that you call it. I hope I'm using the correct name for that. All right, so look. So now we want to find our x bar, y bar. We want to also find the volume of each. So let's look and see how it's done. And then I'm gonna ask you some questions here. All right, so look. So the weight, they want you to calculate the weight. So you know that the density times volume will give you the weight. So the volume, how did you find the volume here? We're saying that the volume would have been what? The area of the triangle here, which is half base times height. So the base is 6. What is the height? And what is the height?
6.
So,
6,
it's
sir.
half base times height times a half, which is right here. And you're able to find the area of the face here, the rectangle face. And why did we multiply by 2? But I want to tell you why we multiply by 2 now. Because we find this is the volume. This is the volume. So this was area of that face times the thickness. And two represents it, 2 right here is the thickness. So that's where you got the volume of that. And for the cuboid, the same principle here. The cuboid, we said what now? We said that the base, if you want to take it from the base is 2 by 6, right? 2 by 6, and then the height of it is 6, right? So therefore you get right. So it depends on how you want to look at it, and this give you. So this is the volume, right? So the thickness, if you want to call it thickness, 2, or you want to call it. So I say the base and then the vertical height. So it's the area of a base, which is going to be 6 times 2. So that's the area, and then the height is 6, and therefore, right. Now we divide by 12 to the cube because we want to convert it from inches to feet, right? And therefore it can work out. Because remember that the density was giving us to us in what now? In pound foot. So that gives you yeah, they're around here. See them there? So right, so those are the density. And as a result, you get those weight. So okay, so those weights are placed inside here. So this is weight now. And then now we can find X bar, Y bar. So let's look at how we find X bar for the area A. So X bar for area A. Who want to tell me how to find X bar for area A? How do you find X bar for area A? This is a triangle. That's a triangle we're talking about. How did we find the
Third,
it's
the
4? How we
1/3,
find 4? Anybody
the
want to?
1/3 plus the
All right, so 1/3 of
2
it is
inch.
your 2. And then the distance from here, yeah, it's a 1/3 times, and then the distance is 2, right? So it's right. So it's 1/3 plus this distance here 2. Let me see. Let me explain it good. So it's 1/3 this distance here. Then you add this distance 2 going to the origin. But the origin is round here now. It's down there. But it is, you can't even see it, it's round here. So it's this 2 here plus this 2. Because this 2 carry to the origin. From this distance to come to here, give you the origin. Here. So that is, this distance is really the 2. So that 2 plus 2 give you 4. So that you get 4 from the origin, always from the origin. And then now y1, or you get y1. Anybody want to tell me? Or we get
The 2 at the side there
this 2 here,
on the
half
yes
of
sir,
it.
and half of that.
Right. And the z, or we get it for the z. The z is going up. And the z, what's the height of the z? 6. So is 2/3
1/3 of
of
it.
6. 1/3 of the 6 give you 2. So it's 2 to the origin round here, round for that face. Right? So the height, 2 says 2. Right? What about x the b now, the cuboid? The cuboid is a little bit easier to see. So you have the cuboid here. Your x is what? Your x is 2. So it's half of 2. You get 1. And for y, how much is it for y? Do I need to clean that up? How much is it for y? Yeah, explain and tell me why y is 3. Can you see it better now? Oh, tell me why y is 3.
Half of the 6.
Half of the 6, because yeah, the length of y along the y-axis is 6. So it's half. Yeah, right. So therefore that is 3. And z is the same thing because the height of it is 6. So therefore it must be 3 also. And you simply multiply each one of them by so this is the weight time x, weight time y. So it shows you that you can also find it of the weight or Yeah, so the weight, so you multiply it, and you see these column here, they're both going to divide, all of them are divided by your weight over here. So you're not using here this time around. This is weight, right? So remember, we told you that it could happen. And see there, so this gives you in inches in each one of them. And that would be the way your central axis happening. But that is 3D, all right? So that's a little introduction to 3D. All right. So that is that. We're not finished. We're gonna discard that. We're gonna open another slide. All right, quickly. And this one I'll have some more information on it. Let's get to it. Where is the slide? Hold on. I'm at the right desktop. Hold on. I think I'm at the right desktop. Let's get to the right one. So that gives you some information. Now we're gonna look at some other stuff that you need to remember about inertia. Let's get to another slide. And by the way, I've opened the slide on Moodle, so you should be seeing your slide, and I'm gonna give you the solution sheet that I have for the question that I'm working. After tomorrow, I'll release it. So where we are now, so we're going into inertia now. Let's look at the inertia slide. I should think that this is the correct one. All right. So inertia now. Let's do a little bit of recap. So we're not gonna go through this. We're gonna jump right into what we need to jump into. Next week, if anything, we look at doing it by integration, finding inertia by integration. Right now, we're just focusing on the parallaxis theorem and using it. So the parallaxis theorem, in previous years, what I normally do, ask the student to draw up the circle diagram here and explain the parallaxis theorem. So if you can notice the parallaxis theorem, this is your centroidal axis. So you get an elemental shape, and we choose to take a little shape out of it. All right? The center between both of them, this is dy, this is dx. So the axis, if you notice, you have x-axis, and this is the axis that is parallel to the x-axis. You see that? So the distance dy is that distance. So if I ask you to find the inertia of around the x-axis, not the centroidal axis, but the x-axis, this is what you use. This is your dy for any figure. If I also ask you to find about y from the centroidal axis, they use dx. And it's different from if I said it's around the centroidal axis. So if it's around the centroidal axis, you would have get between the center of the shape, you would have subtract the difference. But this one, you just need to find the distance from the center of the body to the particular axis, and it's different. So I want to point that out. I started it last week, and I think I actually was working the problem around the centroidal axis, but it's all right. I'm going to show you that shortly. So this now, right? So this is the formula. Let's jump on it. So, and this is how they got it. So this is the one for the, remember that this is the one for the inertia for the x-axis and inertia for the y-axis. What you need to remember, when you find the inertia of the x-axis, you're using the y component. And when when you find the inertia of the y-axis, you're using x component. One of the things, look at it, you see it? You're using x component, and this one you're using y components to find it. Always. So remember that, bear that in mind. All right, this figure here, see this figure here? I think next week everybody should work this figure here. This is a nice figure because this will actually get you in groove for your preparation. All right, I recommend that strongly. All right, now look at this. So what I mentioned a while ago, we have two figures here. You have this figure here, so this is represented your hole. This is a void area, so you know that there are minus, and that you must forget. To find the inertia, remember that you're going to use the standard of the figure first. And for a rectangle, what was it again? Remember what it was? What's the standard formula for the first inertia of your a rectangle? Anybody remember the formula?
Rectangle, sir.
Yeah, what's the first, for the first inertia, what's the formula for a rectangle? The first part, you remember that? So if you have Ix and you're finding, so the first inertia, which is Ix prime, that you find is going to be BD cube upon 12. You remember that? You get that from the table because the figure is a what? a rectangle. So you'll have gone for your rectangle. Once this figure is a rectangle, whatever the type of figure is, the first inertia you find is the standard inertia of the body shape. Then the second one now will have to do with the area times the distance that you consider dy. So for example, in this figure here, your center of it, this would be your dy. Right? And for x, this would be x dy. Now, in the two cases, you'll have to use these expressions twice. So for the circle, you would have to find the inertia for this one. I think the inertia, if I remember right, is 1 upon 4 pi r square. We can check
Pi
that.
R4, sir.
Pi
R4.
Pi r4, right? 4. Yeah, I think something like that. Yeah. So that you check the tables and you get the right one and you put here. So you'd have to, and then now you identify your dy. Your dy here would be the same dy. Both dy for the circle and the dy for this. And if you notice though what is happening here, this is passing through the center of it, where the central axis are. So it's a little bit different approach. Right, so you have to bear those things in mind. But then I will show you the difference and the pros and the cons of it. All right, let's look at this figure. We're gonna do this problem now. Somebody just sent to me that we work it in some tutorial is wrong, and some other class, I think it's my other lower class, saying that this said problem was work wrong. By they say some notes that they have, let's see it work wrong. But I doubt it. It depends on where you're looking from. So let's go through it. They say here the beam cross-sectional area. Right, you must find the inertia of which axis they say here. So why this axis here? And you notice that the y-axis cut the figure is the symmetrical axis, is the y-axis, and it's crucial to the end result of the problem. And this is where your centroidal axis is. Your centroidal axis is end up to be your x prime axis, and your x is up here, right up on the ridge face of the figure, which makes a big difference to how it is. And this is your standard formula. So all the time you're going to be using BD cube upon 12, but of course it depends on where you're looking. You will reverse the order of your B and your D. So one is going to be the B, the B is going to be cube. Depends on how you look at it. So this is for the, normally they find around the X. When you find around the Y, this is how it look. And this is what we're going to discuss now. All right, so let me go back to slide share, and then I probably can clean off this. All right, so look at this clinical. We're going to do this problem now. So if you get a problem like this, I want to know that you understand what is involved. Oh, it's not coming up. All right, I want you to understand exactly what is involved. Discard that, get it off, and come back. All right, so look. So now you are to find this. So, okay, the first thing you do, you're going to separate the figure into some shapes, regular standard shape. And so far, this is rectangles. So you have rectangle 1, you have rectangle 2, you have rectangle 3. Are you seeing it clearly? Now, the first rectangle, what's the diameter, the dimension of the first rectangle? It is 6 by, the length is 6 and the height is 2. So that means the area is 12. So it's 6 times 2, you're 12. So we know the area for that. Now, if you notice the center of it, where your x bar and your y bar would lie, look on it carefully now. So this is the center of the figure. It means that, and normally for a rectangle, you can do that and you see the center. And everybody know it. So this is 3. For 1, you look carefully, but it cuts across here. Remember now, x is right. Where's x again? X-axis is up here. See, x-axis up here, which makes a big difference. All right. So let me clean up that, make sure you can see it. All right. Now, let's look down. It wants you to find inertia. So it asks to find a centroidal axis, it asks to find the inertia, which is different. So let's look on it and see how you find the inertia. So the inertia of figure 1 is going to be this inertia of y prime, times the area times dy square. And if you notice, what is dy square? Dy square is a challenge. Which direction are you going to be looking? So in order to be getting it around the y-axis, because the body is going to tend to want to spin around here. That is what the inertia does to it, give a tendency to spin. So you're going to be...
Inertial y we have right, sir.
What?
Inertial y we have.
Yes, so this is where you're going to be looking. So see your eye here. So you're looking this way. So your eye in terms of the parallel way, the parallel axis to your eye, this is where you're going to be looking. You're not looking down here. So you can either look here to see where your parallel axis is. This time around, you're looking to see where is your parallel axis here. You see what I'm talking about?
Yes, sir.
Good. So one of the questions I want to ask you, where is the axis parallel to your y-axis when you look that way? Is there an axis parallel to the y-axis that you could refer to as your y prime axis when you look that way? Yes or no? In terms of the figure, the center. Yeah, where the central axis would be. So when you look for the central axis is down here. Right? So X have a parallel axis to the centroidal axis. You can see that? Which is X bar,
sir.
X
Yes,
prime.
sir.
But Y don't have one because Y cut the figure in the center. So it runs on the centroidal axis for the Y. You see that? So that is why we call it the axis of symmetry. Because that's a dividing line in the Y, in terms of the Y. Y divided perfectly in equal half. So what's the implication of that? You're gonna go to this formula here, your standard formula. So your standard formula, this now becomes your, I would tell you that in my view, I would just say that this becomes your breadth. The book tend to say that. I realize that the book is using this as H still, but this and then bring this as B cube. What I would say to you, well, all right, fine. If you want to, the book tend to keep this as H, right? But one way I would tell you to remember it is just say this becomes the base and this becomes the height. Once you say that, you can't forget it. Because always the height is going to be what is your cube. And the base is what will be standard. So that's how I remember it for many years. So once I write BD cube, once I'm looking and I say that this is the base, this is my height, so I keep it. In other words, I don't write it like this. So I can remember that anytime for any one of the axes because I keep it standard. I just say base times the height cube. So some people use H. So remember, D and H are interchangeable. So some textbook use B, some use D. I use D, which means the depth. So the depth is always going to be cube. Whatever figure I'm looking on, I'm cubing the depth. And this is my breadth. So I don't really use this formula per se. So I use, this is my standard formula that I have in my head, always. So that's what helps me to remember it at all times. So this is breadth and this is depth. So the depth is always going to be cube. So you can think of it that way. The book just shift them around and said this is H, which is originally H, and this is breadth. So when you're looking this way, you cube the breadth, the base, and keep the H. That's what the book does, but that's how I'm telling you what I use to remember it. So you can choose to use any which format you want to remember it. But remember, you're looking that way. That is my by way. I've always tell the student to look two ways. So this when they say why, and guess what? Look, the components that are useful to you are not the y components. They are all x's going across. All of these distance coming across are all x. You can't quote any y because the y is vertical and the x is horizontal. So these now, when you're looking this way, what is this way to you now is the x. The x is what is relevant to you around this axis. In other words, the x, from your base of the figure, if you want to still call it base or whatever, this distance here is going to give me the radius that the figure want to tend to rotate around this axis. See there? The figure it will rotate around that axis, so what is the radius? The radius must be 3. In other words, you understand me? That is what I use. So when you look at the formula down here, this part of the formula falls off. Why is it that it falls off? Because there's no dx square. There's no distance between the centroidal axis and the axis that you find about, because the axis of symmetry. So when the axis of symmetry come in, you have to drop off dx. Once it goes around the centroidal axis. So if it's x, you would have done the same. If it is y, their dx automatically drops out, because there's no distance. The dx, the distance that you want, right? Because you find it about the y. You see, if y was over here, it's a total different thing, because it would have a dx would be this distance, and this, let's say that was the centroidal axis, and this is your y. That was y prime, and this is y. Then you would have a dx. But because it drops at the center, you don't have one. Right? I hope that explains it well to you. So as a result of this, that goes, right? And you just use this standard formula. So I would say breadth times depth cube. That's what I've been telling my students for many years. So, and that helped me. But if you want to keep it standard, because this is really the height and this is really base, but you have to remember that this base is going to cube when you're looking in the y direction. So the b is going to be cube, and the h is going to be like representing the base, right? So I tell my students look that way, and it's easier to do the problem. All right, so that is for that part. So I spent quite a bit explaining that. It's important. Let me move on now to C2 and C3. As you can see, C2 and C3 have the same dimension. They're both 1 here, and they're both on what, 4 in the height. So if you find 1, you find both. You just double them, right? So some people generally just find 1 and double it by 2. So it's I1, I2, and I3 are the same. So you basically can add them to you. You find 1 and you get the same value as the other. All right, let's find I2. So see I'm showing you here. Let's find it now. So this one is with the standard formula, which is your BD cube upon 3. So this here. So this is if you want to call that I cube, fine. And you call that base 1. Or if you just want to switch them around and say that this is a base, that is the height. So you know this distance here is cube, and that distance is it. So you depends on how you want to remember it. All right. So here they have it for the first part. The next part now, the area is 4 times 1. So we know that that is standard. What is your dx here now? How do you find dx? Can somebody tell me how we're finding dx here for this figure? So remember, your central
the centroid for the C2 is
down here.
Is 1, yeah.
Right.
And
so
then the distance along the x is 1.5 from it.
So look, yeah, because half of this is 1. So half of 1 is 0.5. So this little distance represents 0.5. So then now the distance from the y-axis to this part of the figure is 1. See here? So this is 1. So it's 1 plus 1.5. So this is now become your dx. So it's from the center of the figure to your y, give you your dx, right? So remember that is finding it to dx. So you don't have to subtract anything. It's just the fact that this distance is halfway this distance plus this. So it must give you the total length is 1.5. So 1.5 square. All right. So let's jump on and leave it there. Right. So that you just let me see. So what you do here, you'd simply add. This value would be 9.33 and 9.33 plus the one that we did before, which was what? 36. And then you put 36 and you add them together. And none of them are negative, so they all had positive together. And note, the unit is what? To the 4th root. If you miss that, you miss it. So the first one you find, you're gonna get it to the fourth root. Whatever this work out to will to be the fourth root. Whatever this work out to fourth root, and you just add them, so you get it to the fourth power. Remember, always. All right, so let's run on. All right. How much time we have now? Because I want to go through something. We have 3:11. All right, I'm gonna use 10 minutes and try and go through something else, and then we'll start the tutorial question. So let me introduce you to what we call inertia of mass. Right? Don't know if we're gonna have time next week to do it, so I'm doing it now. All right, so the mass moment of inertia, right? It is really finding mass moment. So we're gonna be able to explain what is mass moment of inertia, which we call MMM. Just like how you find it for area, you can find it for length, you can find for mass, and you can find for volume. But we're dealing with mass. All right, so determine mass moment of inertia. We're going to look at the application here quickly. So we're not going to spend too much time on it, but I must introduce you. So you have this flywheel. Flywheel in the picture is, and are you seeing it good? So the flywheel in the picture is connected to a large metal cutter. So the metal cutter up the top. The flywheel is used to provide a uniform motion to the cutting blade while it is cutting the material, right? What property of the flywheel is mostly important for this use, and how can we determine the value for this property? Anybody want to tell me what's the property? Just think about it. So why is most of the mass of the flywheel located near the flywheel circumference? That's another question.
Torque.
Torque. Beautiful. Hallelujah. Because inertia and torque have a combination. You know the formula that combine inertia and torque and angular acceleration? All right, coming up, we're going to look at it. So, all right, we're coming, you're going to see the formula shortly. So, here we go. So, what about this? Also for a fan blade, the fan that you have in your house, if the torque M is applied to the fan blade, initially at rest, all right, its angular rotation begins to increase, right? Once you start it, all right? Which property, and it's have in bracket here, which we will call P, some property P of the fan blade do you think will affect the angular acceleration of the most, right? So O is the origin, and it have a mass coming around. So the fan blade will have a mass, and it will rotate around that point and your fan that you have at O, right? How can we determine a value for that property? So there's a property that will cause, will affect it, how it rotates around that. What is this relationship between your mass, the property, and the angular speed? You know what is P? What do you think is P? Anybody want to guess?
Distance.
Sure is distant?
Or
Are you mentioned it before?
What the torque?
No, well, the torque.
Or
what is connected to the torque and the angular acceleration? That we just been mentioning, right? It's the inertia.
Like
the both, yeah. So inertia and the mass have an effect. So that property is there. Inertia is one of the property. All right. So the mass moment of inertia consider the rigid body with the center of mass G, and it is free to rotate around some axis Z axis, right? Which passes through G, right? And that is the center of mass of the body, right? Now, what they're saying here, now if we apply a torque, just like we talk about the axis and the Z axis to the body begins to rotate with an angular acceleration called alpha. So the torque and the alpha are related to the equation. So the inertia is that property P that combine both the torque and the angular acceleration. And the inertia have something to do with the mass, right? So this equation is the mass moment of inertia, MMI, about the Z axis, right? So that's in the equation I, right? So the mass moment of inertia is a property that measures the resistance of the body to the angular acceleration, right? And this is similar to the role of what? Newton's second law. But remember what Newton's second law is? Force is proportional to what?
Hence acceleration.
And therefore that is how we get the formula, you know, and how we get rid of the proportionality is the mass, which is the constant factor. So therefore force is equal to ma, which is the second law of Newton. So the mass moment of inertia is often used when an angular rotation mode, analyzing rotational motion. All right, running from that now, quickly. So consider the rigid body of an arbitrary axis P shown in the figure. So you have some arbitrary axis rotating. You have the mass moment of inertia about P axis is defined as I, right? So the inertia, as we're looking at, we look at next week, in terms of integration, it is R squared dm. We won't spend much time on it. Kind of come in an exam, but I'll just introduce you to it. One or two little questions. So the moment so R is known as that R square here is the moment and it's a perpendicular distance to the axis to the arbitrary element dm, right? So it's a look. So you see it's a perpendicular distance and the moment arm is right here, right? And the right angle is here. So the mass moment is always a positive quantity and as a unit of kilograms meter square or slug foot square, right? I'm running. All right, so the parallax theorem for mass moment of inertia. So just as you have mass moment of inertia for era, and your parallax theorem can be used to find it. The MMM about the parallel axis of the mass moment of inertia about the parallel axis Z, that is the distance D, see it right there, from the axis, the Z axis through the body center of mass, G. So it's related. So the formula for inertia of the Z-axis, right, taking in respect of the inertia of the mass at the center plus the mass of the body times d square. Now d square is something that you have to look to see where is your d square. Sometimes you have to use Pythagoras theorem to find it, and we'll show you in the problems that you have there between now and next week. So where m is the mass of the body, the radius of gyration. So this is another engineering quantity that you need to know about. So k is equals to the radius of gyration. It is really the inertia divided by the mass. Just like how for era, it's the inertia divided by the era give you the radius of gyration. Right? So finally, the mass moment of inertia can be obtained by integration or by the method of composite figure. So we won't get into that. We'll just show you the regular of composite figure. So we have two things to introduce you to because, so we're gonna spend both 5 more minutes on this and then we'll go over to our question. So given the pendulum consists of, so here you have a pendulum. This is a sphere, this is a cylinder, all right? And it's anchored up here. The pendulum consists of a slender rod. So the rod is a cylindrical bar with a mass 10 and the sphere has a mass of 15, right? The pendulum mass moment of inertia an axis perpendicular to the screen. So it's perpendicular to you. You're looking at the paper, there's a line perpendicular to it, to the screen, and passes through O. That's where the mass moment of inertia about an axis that is perpendicular to the screen. So it's perpendicular to us, right? And it's coming through the point O up top there. All right. So let's it says follow the steps similar to finding the mass moment of composite shapes. So you're gonna separate it into what we know. This is a cylindrical area. So you separate it into cylinder and you separate this into a sphere. So two things you separate it into. So the wheel can be divided into the slender rod and the sphere. All right, so let's look at it quickly how this one is done. So the center of mass of the rod at point G, right? So look, so point GR for the rod that is, right? And they saying that the distance there is half, 0.225 meter from point O, right? So that from point O, that is the center of it. The center of mass of the sphere, you add both of these things together. So this is the radius is 100, and you add that. You get 100 and you get 550 millimeter. You divide that by 1,000, you get 0.55 meter from O, right? So both of them are measured from O. Remember, the axis that we find in is perpendicular to O. All right, so the mass moment data for the slender rod and spear are given as a formula sheet. So you have to look at the formula sheet for this. Now, using the data and the parallaxes theorem, you can calculate the inertia of the from O, right? So the total inertia from O, this axis up here, for G, inertia due to G, center of gravity, for both figure, is going to be mass times d squared. So for the first one, for the slender rod, you look in the table, you will find that the formula, as I was showing you before, is 1 upon 12 times the 10, the weight, the mass. So it's going to be mass, so it's 1 upon 12 m times r squared. R squared is, how do we get r squared? Anybody want to tell me how we get r squared? So r squared is a radius, right? And that's for so see here. So if you notice the distance, this distance coming down to here. So that is that distance. It's 0.45. So that is your d. So your d is right here. Come down to where you touch. So that distance is d, and you square it. All right. So you will see in the table your r squared. So that this is become your r squared. Right. So that is the formula. So the formula is 1 upon 12 m times r squared. Then now for the second part, you multiply the mass of it, which was given was what? 10. So it's 10 again times the d squared. So this d squared now is a different so this is radius square, which is this is what they call the radius. And this now is going to be half of the distance from here to there, which is 0.25. So see, I gave it to you. See, that is your d. And also for the spear now, you're going to do the same thing. The formula is different though. It's 2/5. You'll have to look in the table for it. 2/5 times the mass times the radius. So the radius here is 100 millimeter divided by 1,000. You'll get 0.1 square. Then it's going to be the mass of it times the distance from the top right down to the center of the body. Just similar, which is 0.55, and you square it, so you get that value. So the total inertia due to the mass, the body, is going to add both the one for the slender rod and the spear, and you get that value. All right, simple as that. And this one is similar, but the formula is different. You're going to even find the radius of gyration for this. Let's look quickly how it's done. It's done. So first you have a rod here, and you have a plate here. So the plate has a dimension of 1 times 4, so the formula is different for a plate. So the same thing will happen here. You can find wire bar if it's not given, and it's the same kind of principle. So you go and you look for up here, this part here, you look for your y component for each one. So for this one, your y would have been, the center of it is 1. Right, times the mass of it. The mass was 3. Right, so the mass of this bar here was, see, 1 is 5 and 1 is 3. So it is 1 times 3, right, plus so that is for the center of that. And then now for this one now it's going to be 2.25, right? So it's 2.25 is from the distance from up here to down here. That's 2.25. Wait, the mass, let me go back again. I'm going too fast. So that is 5. The weight was 5, and that is 3. All right. So you multiply the 2.25, right, which they had given you, so it comes somewhere down inside here. Right? So the G is somewhere down in here. 2.25 times 5. This was actually given. See it up here? The rod. So that is both the rod and the plate. So it's multiplied by the 5. And of course, the weight of it, you divide by the sum of the weight of it, and you get. So you get that the Y bar is 1.781. Right? And then now you would go to your formula sheet for each one of them, for the slender bar or the pendulum or rod, whatever you want to call it, and the plate. So for the the plate, it is going to be 1 upon 12 times your height, if you want to call it that, square. As you will see, the formula sheet says, so this is the height here, so square, they probably call it h square, l square, plus the length of the base here, square. So you look in the formula sheet and you'll see this. And here now, the mass is what? 5. So you're going to subtract this distance here, 2.25, from this distance given here. And that is given here, d square. And then the last one for the cylinder bar, see 1 upon 12, this is a cylinder bar. So it's mass times r square. So the length of this is, so that is, what is it again? It's 2, right? So you get that. But this one now is this distance here minus 1. Remember, this y1 was 1. So it's 1 from this centroid axis. So you get that d, right? And you get that value. All right, so that's it for, right? And then you just simply add them together. You find radius of gyration. Once you get this, you divide by the total mass. You get the radius of gyration. All right, let's go to our tutorial question, guys. That was just some information for you. You can read it up if you have any question. But most of those information is on the table. Let's go to your tutorial sheet now. I have it pre-done, so I'm gonna just go through it and we'll walk through it. Where do I find it now? This look like it. I think I have it here. No, different one. Last year, that was that tutorial sheet I did last year. Going back to the tutorial sheet that, where's it now? See if I can find it here. Tutorial sheet, yeah. All right, I think this is one of these. Let me see. Is this it? Let me see if this is it. All right, beautiful. This is it. So yeah, so this is your tutorial sheet that we're looking on from last week. So we would have gone through and we did most of the weight calculation and all of that, and we found the mass of it last week. Everybody remember that? All right, so we did the weight. Question wanted you to determine the mass, and it also wanted give you a number of things. So we define the mass of it. We're able to find the area. This was a void area which divided, you get the total area here. This was a semicircle. You separated it into a big rectangle and a small rectangle. So we're gonna look at it in a little bit clinical way now and finish up. So we have those already. You remember how we found this? Let me just recap you. We separated this into semicircle. We have about half an hour to go, right? So we have I don't think I can write on this. Anyway, I'll just explain to you. So this is, I don't know where to find the PowerPoint for it. I know I have the PowerPoint for it. I don't know.
I remember this.
Pardon me?
Yes, I remember this, the semicircle and the
Yes, so this is
rectangle.
the semicircle. I remember, oh, you find y bar for the semicircle, it would have been y, the same 4 upon r divided by
Yes,
2 pi.
yes.
Up at the center here, if you can see my pointer, up here, so you would have find that little distance up here. I can't write on this thing, I don't know why. It's not allowing me to write on it for whatever reason. So I can't write on it because it's a PDF. All right, so we are able to do that. Let me just recap here. So we found this little distance around here, which is 4 upon r 3 pi. You got that distance. And from that distance, we're able to add that distance to 5, right? So this semicircle, that's y bar, but r x bar was 3. So your y was that distance, 4 upon 3 divided by 3 pi. So that was your y bar. And then your x is a 3. So we're all right with that. Let's look at the other part now. So the large rectangle, it was what? It was 5 by 6. So your y bar is 2.5 because your height is 5. And for your x, the length is 6. The half of 6 give you 3, right? So you get so you see where your x and y lie for that. For the void area now, which you know is a negative area, the base was 4 and the height was what? 3. So half of that distance is, so the half of here is going to be what? 1.5, half of 3 is 1.5. And then now, the distance, half of the rectangle base would be 2, but to carry back to the origin would be what distance? What distance would carry back? So what's your x value? And what is the total y value? Yeah, what's the x value and the y value?
Let's see now, the 1 plus the 1.5 and no, not the 1 point.
Between
what's that?
1.5 plus
Yeah, 2. The 1 plus the 2.
yes, 2
1
was
plus the
down here,
2,
so
and then
down
for the
here, so
x,
this distance
yeah.
was 2. You remember that? This distance down here, so
2, sir.
between the void area was 2 down to the x-axis. From the void area to the x-axis was 2, so it will be 3.5, and then x is always going to be 3. So for all of the figure, then x is 3. All right, let's look at it. So we have the solution. So here, so you'd have gone through, and in the table here, see it reflected here, look. So the semicircle area you put here. If you notice, so the void area, you put minus in your box. For all of them, so the last one there for the void area, 2 plus 1 is x, so it's 3 also. And I'm doing the last column first. And then the y would have 1.5 plus 2, so that is 3.5. All right? And you keep multiplying the area by each one of them. So you notice you get ax y to minus 36, and no, ax bar would be 36, and ay bar is minus 42. And both quantities are minus. Note that. All right, for the rectangle, it will be 3 times 30, give you 90. And for the other one, it will be 2.5 times 30, give you 75. Those are positive quantity. And the other one now, you'll have multiplied 3 times the area of the semicircle. So C, we have a value 42.421, and the other one would be 5 plus 1.27. Remember that the 4 times 3 divided by 3 pi by about 1.27. Everybody remember that?
Yes, sir.
Plus
1.27.
5.
3.
Right. So that is going to be that distance times the area, and that works out to be 88.6. So you simply add the columns them. Make sure that you subtract what need to be subtracted for all of the columns them, and see the answer them up here. So look, x bar is just proving to you that it is always 3 and it's going to remain 3 for all of the figure. And then y now is going to be 3.8. So you can look and see your y bar is 3.8. All right. So as they say, it is possible that the centroid can be located in the void area or the negative area. All right. Let's move on quickly. Now, last week we started this, but I think when I looked at it, I didn't read it properly, and I think we started to do it about the centroidal axis. But it's not that they ask you for, they ask you about the x-axis, and there's a difference, guys. So let's look at this now. Afterwards, we can look at the one about the centroidal axis. I think it's on the slide. So here now, you're going to determine the area moment of inertia of the shaded area about the x-axis. All right? Can somebody tell me how you're going to approach this one? Before we even start look at it, how is it that we're going to approach this one? You're still going to separate it into the different areas. So you're going to have the semicircle, you're going to have the void area, and the big rectangle. Pardon me? You saying something? It came to
No, sir.
Yeah, right. And let's look at how you do it. But you're gonna have it up. You're gonna find about the x-axis, and it make note of this, guys. Make note. Look. So this is the parallax theorem. You find about the x-axis. I cannot write on the slide because it's not permitting to write on it because of the time. I'd have to take it and go somewhere else. And in the interest of time, I'm not gonna do that. All right. So if you look at this carefully now, right? Unless I open it, what if I open it with a different thing. Hold on a second. Let me just try something. It just occurred to me that I may have a writer in a different thing. Hold on. I'm gonna open the same file with Outlook. With this one here, Edge. And maybe we can write on it with Edge. Let me see. I think I can write on it with Edge. All right, where are we again? We get back to it. I think I can write on it with Edge. Edge will allow me to write on it. Just occurred to me. Your bright sparks couldn't tell me that I must use Edge. All right. So where are we now? We're looking at the one with the x-axis. Yeah, right. So we're right here now, and his x-axis that we want to find about. So we're gonna use the parallaxes theorem. And let me tell you, I think I can write. Prove myself wrong. It highlights, but I'm not seeing a writer. It looks like it's writing. Yes, man, can write. Beautiful. All right. Because I can sign stuff. Yeah. All right. So here you use the same parallaxes theorem. So right there now, you see that is the first one. So one. All right. So the moment of inertia around the x-axis is down here. So it means that you're going to operate from within the center of each body around. So your dy's are going to be from each center. So the center of that, the center of this one, and the center of that. So they're going to be different. The three centers, wherever the centers are, will operate for your dy. So let's look on it and see how it's done. And this one is different from the centroidal axis. So we're going to find the moment of inertia about the x-axis, not the x. So look, the centroidal axis was what? 3 point, what was it again? 3.8. So it would have been an axis like that. So that was your y bar. But it's not that you want to find about. That will be the y, this will be your x prime axis. But it's not around here they want to find. They want to work from the center of each figure. So it's like say this figure here, your y for each figure would be this. So this is y1. Let's say I want to take that. Y2 would be a distance from the center of the rectangle would give you your y2, which is your dx. And then the other one would be about 25, 2.5, wherever the 2.5 comes in. 2.5 will be about here. So the 2.5 would give you the next the dy 3. So d2 would be this one. This will be dx2, no, dy2, sorry, because y component. And this will be equal to dy. So that is an int. That's different from the, so let's go and look and see how it's done. All right, so look. So the first one is a semicircle. So for the semicircle, what will happen here for the semicircle? You're going to look in your table for semicircle inertia, and you see its value here. Beautiful. So this is going to be 1/8 pi r to the 4th. That is the inertia of the standard inertia for the figure. So that is this part of the equation. Remember? That part of the equation. The next part of the equation is the area of it, which is going to be half of a circle, which is pi r squared divided by 2. See it right here? And then now, you need the distance here. This was what? 1.27. So we work out all of this is 1.27 plus 5. That was 6.27 approximately. So this distance is that d there now. So the d there now, your dy that I'm talking about. So that's your dy. So everybody get that? And it's around, so it's going to be rotating around which axis? Around here. Right? Around this axis, you're rotating around that axis this time around. Is x-axis you're rotating around. So that becomes your d, and it's different from the centroidal axis. The centroidal axis is where would have been where the 3.8 is. So it's not around that axis you're rotating it, you're rotating. So you have to look for the particular axis that you're asked to rotate it and find the d related to that. So it's 1.27 plus 5, and you get that distance there. Any question there so far, guys? Is that clear?
Clear, sir.
Yes,
Yeah,
sir.
man. Yeah, man. I want to know so it's clear. All right. All right. So and that is for the semicircle. So therefore, that will work out to be that. You can test it. You'll get this information. I'll send you this so your body read upon it and make sure that you understand it clearly. All right. The next one now we're going to do another one. All right. We say the large one now. The large rectangle. Let's do the large rectangle. The large rectangle, what's your standard for the large rectangle? And you find about the x-axis, so the standard BD cube upon 12 stand, or BDH cube, whatever. BH cube if you want to use. But this is my standard one. This is what I remember. All right. That has been engraved in my memory for many, many moons. All right. So that formula is a standard one right here. Then now you're going to find the area of it, which you already know is going to be what? 30 is 6 times 5, 30. And then now you're going to find your dy, which is coming from where? Half of it. See it here? It's your dy that, and that will rotate around that axis there. So it's tending to the body rotate around there. So that gives you the inertia. The inertia is resistant to rotation. So see there. So this is 2.5, pardon me, and that's a square. This is the area times 2.5 square. Right? And therefore that works out to be 250 centimeters to the fourth. Note the unit. To the fourth unit. So this is B D cube upon 12. All right. Let's look at the void area now. The void area quickly. So the void area is this, which is going to be what now? It's a rectangle again, so it's BD cube upon 12, not true? Right? And then you have the area of it, which is going to be what? 3 times 4, 12. And then you have this distance here now. What is this distance here? It's going to be the distance that you work out before. What was this distance down? It's y bar. Its y bar this was 2. You remember that was 2? So it's 3.5. 3.5. Perfectly well. All right, great. Great that you see that. All right, so, and this is what? But this inertia is, all of it is a minus inertia. Big minus.
Because it's a void.
Yes. So the total inertia is going to be a minus inertia, and you add the rectangle, add the semicircle, and you minus it. See there? Minus. And you get it. Perfectly well and done. All right. Now, what about if they ask you to find about the y-axis? Let's look at it quickly. Quick. So if you ask you to find about the y-axis, you use the same expressions. If the semicircle, you use the semicircle formula, you do the same thing, but the only thing you're doing, your dx is different. Your dx's are different, but this way you're looking. So your dx, what will be your dx? Your dx is 3. Right? You realize that your dx for the semicircle will be 3. So all of them would be 3. All of them would be 3. You see that? For the semicircle is 3. See there? Dx is 3. It's around this axis, you know. Your body want to rotate around this axis from the center.
Oh, yes, sir.
Yeah, so that is, so it's 3 there. So it's the same formula, but it's 3. The area of it times the d. Next one, rectangle, large one, your d is 3 again. See there? 3. All of them is 3. That's the only thing changed. But it's this way you're looking. Remember, guide rotating around. So it's from the center of the figure to the y-axis. All of them is 3. Same thing applies, same standard expression. Only thing different. Let me mark you. What is different here? These shift around. Because this becomes the regular side and this becomes the cube side. This side here is the cube side. See it here? Them switch around. That is what is switch around. See it there? And the next one is the same thing. See it switch around there again too. See it switch there. Alright. And this one is the same thing. This would have been 3. So all of them is 3. right? And that is the difference. All right. They say find about, so so all you have done is add them here, right? So you just simply add them and minus the void area. The void area is this one. But this one don't work out, you know. You can work that out. When you get it, you can work them out if you so desire. All right. Last one to go here quickly now. It says, determine the moment of inertia of area about an axis parallel to the x-axis passing through the centroidal axis. This is the one that I really want to explain. So you're running down so far. So this will have been your axis. This is the x-parallel axis and this is the centroidal axis, which is parallel to the x-axis. And it makes a big difference on how you approach it. So come, let's look at it right now. So that is the figure and the same standard figure. The first one, the standard equation would follow for our semicircle. The standard area. But look at the distance now. Let's look at it. So the semicircle, your distance to down here was going to be what? You remember that it was 1.27, right? Plus 5. You remember that distance there, so it was 6.27. Was that D coming down here? So you remember that distance there?
Yes, sir.
Good. So it is that distance minus the centroidal distance, right? They actually work it a different way up here, so but it's the same thing. So it is going to be 6.27 minus 3.83. You get the same value. So that will work out to be what? That will work out to be something like what that now? 2 point something something. Check that out. What's the value there? Give me a value. And add those values and tell me if it's not the same thing. So that's another way to look at it. So the actual
you get 2.47. Yeah.
And this will work out to be the same thing. So let me tell you how you get it. Look, this is the distance that you need. This is your D. This is your D1. dx1. That distance right here is that distance. See there? So you see it's are two different things though. Can you find it about which axis? This is your x prime axis. So it is rotating around the centroidal axis. So you see the big difference? Who don't see it for me? How much are you inside here now? 5 are you? You see the difference? Who don't see the difference? Tell me. Any clarity there? Why is it that it is not 6.27? Because
one is from the centroid.
Yes, it's from the centroid. So you're relating the center of that to the centroid position. You know the y. You see the y that you find first, you're going to make sure that you take away the centroidal y from that distance for that one. And that is how you find it. So that is it. So they work it out because what they did, I think what they have and how they get the 1.5 here. If I think I figure out how they do it, what she did was, who had worked out this slide, I think what she did was to take, where's the 3.8 now? Let me see how she did this. She knew that this was 1.5, 1.27 already. And then now what she did probably was to say this half is this distance here. This was what? This was this is 3 point the distance here for this thing here was let me see how she did it. I'm trying to figure out. I think this is 1.5 from here. And then she worked out a way to get the 1.2. You can look and see how she get the 1.2, but I know how I would work it. Because then it's not a rocket science. Take the distance from here, come right down here, right? And then you subtract this distance from it and you must get that. So what she did, probably, I'm figuring it out. She take 3.8 from 5. Look, this is the distance here that she had to it. This is distance here. So she take 3.8 from 5 over here. And she get the 1.2. And then add to that distance. So that give you the 1.2. You get that? So that would have been 5 minus 3.8. So that's another way to do it. And then you add that distance to it. But you don't have to go through all of that. take that distance, always take the y distance when you work out for each figure and subtract it from that. Or is it that you're going to use a y distance? It's either you're going to use a y distance or you're subtracting it from the centroidal distance. Two ways to do it. And if you want to do that, you're good to go. You don't have to look like a magic to find out that little distance. So it's always going to be, remember now, it is always going to be the distance. This distance here is that d that you're looking for around the centroidal axis, and it's rotating around that. All right, let's move on. I think you get that one. Let's do the large circle now in close to our time. So then you have, because I have a presentation shortly, maybe another half an hour or so. Anyway. So it's 1 upon 12 BD cube, right, which is the same standard formula that you use as a rectangle. So that is for the large rectangle, which is this distance, all right, coming out. So it's standard one you're using. So it's BH cube or BD cube, whatever, standard one. Then now you get the area of it, which you know is 30 in your case. Watch this now. So it is the centroidal distance. Beautiful. So its centroidal distance is greater. What you want is a positive value. You know, your dy is supposed to be a positive value. So it's all you need to do is get a positive value. You're not looking for any negative value. You mustn't get, it's just a difference always. So now look, half of this is what? Half of this is y2 was what? 2.5. You remember that? For your big figure, you know, it was 2.5. You don't remember that? So it's that distance from this. So you see it? You can't go wrong from one to. So this would have been your y2. Because that would have been the next figure that you once you get in your y1, your y2, and your y3, and if your y4, these are the distance that you will work with. Is that again use these as your dy, or you're going to subtract these from your centroidal y bar? Who get the gist of what I said a while ago? Anybody want me to further clarify what did I say a while ago?
Should be clear, sir.
Because look, I'm going to show you up in the table. We had a table for this, right? Let me see. Did we have a table for this? I'm going to show you something. So you don't have to go anywhere far for these values. Look, this is 1 point. This is 6 point what? That's what 6.125 or something like that. This is 2.73. Yeah, and this is 2.5. So this would have been your y. So this one for the semicircle would be your y1. See, this is your y2, and this is your y3. Those are the values that you're going to use. Are you using these for your dy, or you use this one for your dx? Right? Is that are you going to subtract them from the centroidal distance? And in this case, when it says around the centroidal axis, you must subtract them. Where are we? We're at the, where would we? You know what? We're going to go right back to where we were. We went so far. Where we were. We were at this one right here. So you are finding it for the big rectangle now. And half of your y2 is 2.5. So you can go back on your table and identify them, you know. So this is y2 from your centroidal distance, which is y bar. Give me my dy2 if I want to label it that. Because, and it is, look at the distance that I want. This is the distance, you know. See that? Because I'm going to be rotating around which axis? The centroidal axis. So this is my dy2. That's the difference. So if I say I want around the centroidal axis, do not find it around the x-axis. It's around here. So you're going to do some subtraction with the y's them from this, from y bar. Who follows me? I hope that I'm loud, absolutely loud and clear. That is how you get your D. All right, let's move on to the next one. The void area is the same principle. It is in a small value. So what is your y3? What is your y3 value? Everybody remember what was the y3 value? Was the 3.5?
3.5.
Ah, so therefore, see your y3, see your dy here? That's the dy3 you're looking for. So it's going to be the distance between the centroidal distance. So this time, there, that's it. And what I want is always a positive value I want. You want no negative value. Good? All right. So that's how it looks. So that is what you do. So once you get those values, if you notice, the only thing that you'll be changing, you're using standard formula here. Standard formula, your breadth and your height cube, and your area times those distance. And you just simply now, remember now, of course, this is a minus. Always minus same way. Because you have to remember that. If you're looking, if you don't remember, scan your table to say what was minus. To just recalibrate your brain. So see there? So you add this, the large circle, the semicircle solid, and you minus the void here. And you're finished. And so you get the total, whatever. And you guys can work that out. She didn't work it out. She just put the formula there, and that's sufficient. So when you get, we'll send you this sheet. I'll try not to mess it up to clear it off. Right? I think for ones I don't save it, it don't save on it. And so, all right. So down here, let me just take 5 minutes of your time. To get the mass moment of area, which I could actually do next week too, is determine the mass moment of area of the shaded area to the Z. What they do, for each figure, you employ the standard formula. So this is 1 upon mass time R square. R square is your radius square of your circle. This is 3. So see there, and your mass of it, we had found the mass of this part here. I think for the first, we found the rectangle mass. Oh no, we didn't find the mass. You would have to take the. You remember we found the initial mass of the entire body. Do you remember that? Last week we found the mass of the body. And we did the conversion. Remember that we used the density times the volume, and we got the mass? You guys don't remember that?
I don't remember if we did that.
Yeah, we did it.
Yeah, yes sir, we did it.
Yeah, man.
Yeah.
So what you do in this problem, what they do, sit up here, and you're asked to do that, and they do the calculation here. So what happened in this part here now, when they're asking you for the mass moment of inertia, which is the new part that I just told you about, I can repeat it next week. What I do here, forget the last piece. Oh Lord, where have I gone? Where's my file? Oh Lord, I have too many files open. Oh my goodness me.
Sure, the last one.
Last time. All right, let me see. I'm coming back. I think I'll find it here. Yeah, so here now, yeah. Telling me that is 4 o'clock. In half an hour time, I'll have a presentation, but it's all right. I'll just finish up with you. So here what happened now, right? I don't know if I still have the writer. Am I still having that writer? No, I don't have the writer. Because I'm in the wrong file. You say it's the last file?
Yeah.
Good. All right, so what happened here? What happened here? Let me just talk to you quickly. So this is the inertia of the shape of the figure, which is 1 upon mass times radius square. That is for the semicircle. Times the mass of it times the d. But how do we get the d? So the mass of it, first of all, I was telling you about the mass here. The mass here is going to be a ratio of the total area. So you're going to find we had the total mass, total area of the thing. So it's a ratio between the total area times the area of this piece here. It's a ratio between it. So it's a fraction. So you'd put the area of this upon the total area, right? And you get a ratio and you multiply it by the mass, and it will give you for this second section. So if this was, say, if the total thing was, say, 30, this is 5, you'll have put 5 upon 30, which give the ratio of it times the mass, the total mass. So it would give you the mass of the second section. So it was ratio and proportion. for it. All right. So I'm gonna send you both sheets. I think I have the solution sheet to send you. I'm gonna send you this one, that one. So you do a little ratio table, and you'll find the mass of that piece. And then now you'd find this part now. This part now you'll have to use Pythagoras theorem. So it is a distant here, which is a y distant, x distant, and you get distant here d. Right? So that distant d, right? Pardon me. I'll return that part. So what you'll get here is you'll get here this distant here d. So this is your d. So when you do it, this is your d. Whatever distance you get there, or your square of that distance, you just multiply it. Because the square of this distance is the same d. Whether or not you root it and put back it as d square, is the same d square you get here. So this is Pythagoras theorem. So it's this square times that square give you your d square there for that value. All right, so you get that, and you multiply it by the mass, and you add it, and you get the first section, and this is a mass moment inertia for that piece. So that value is that, and then now the next piece you do the same thing for the large rectangle, but the formula is different. So for the standard for a rectangle is double the width times the height is so here we are. So it's the width 6 times the height square times the mass, and you'll find the mass of that section by using the same ratio. The ratio of the area of the figure. And you get for the rectangle, for the large rectangle. So you get both mass that way, and then now you use the same pi r square to get that d. Because remember, so the z-axis is pointing into the paper, perpendicular to you. So it is going to be 3 times, this was what? 2.5 square, 3 square. And then you get that value. So that will give you that value and the mass. And you do the same thing for the other one, for each figure. This one was what? 3.5. This one is 3.5 times 3. And so that is 3 square. So it's pi r square, and you get that mass for each section. So you need the mass for each section. So you use a ratio of the area times the original mass for each section, and you'll get it. So that's ratio and proportion. And you subtract them just like before for mass, and so you get that. That's the overall inertia of it. Right? And then you can simply put them. You can also put it in the table and do it. So those are your right. So you can do that, and you can put them in your table. All right. All right, gentlemen. And there's any lady, I don't know if just drop your name in the chat for me, please, so I can record the persons who attended. Thank you. Yeah, man. Drop in the name, and then we'll just sign out. All right. So we need to discuss revision. Going back to, and remind me to send you the past paper questions. I'll have to prepare it, because they're not, I can't just take them up and send them like that. I have to know what I want to give you. I'll give you the most relevant past paper that I have. I don't have a problem. I can't get the full paper, but I'll give you some questions from the past paper to practice. Right? And I need to work some questions with you, some important questions that I want to go through, so you know how to. And next week, I might do the quiz. If I give me a quiz, I might do it online. I'm not absolutely sure yet. I play it by the ear from now. The last week of school, if you guys want, we can have a revision class face to face with everybody. Come in and just do a workout on questions, different type of questions. All right. So you also can discuss that among yourself and let me know if I'm early. All right. I'll make myself available in that week. All right.
Yes, sir.
All right, good. So have a good one. All right. Anything? Everybody do the quiz them already. I'll try and give you another one for this weekend. It's probably going to be on Centroid, I think, or the last, inertia. Probably, I think it's maybe inertia. One of them. I'll give you a 7 quiz this week. And all persons who don't get to do the quiz before, do your quiz. There's another one open. I reopen it. Not many persons did it, so everybody can get to do it this weekend. All right. And who want to come to the tutorial class tomorrow? Feel free. Right?
Okay.
All right. All right. Have a
Yes,
big.
sir.
All right. Good. Good. Sure. Bye bye. Remember to drop your name in the chat, please. Before you go, how many persons drop their name in already? Everybody? Let me just check before I close out. Oh, I'm seeing my host tool now, after all. Right.